We've done two things in this unit so far, one being the cathode ray tube, which was Thomson's way of discovering the electron, and the second being the oil drop experiment, which was Millikan's way of finding the charge of an electron. I'm going to draw these two a little bit smaller than I've drawn them on the first day that I did them, because I want to put them both on the same page to draw a couple comparisons here, okay? Firstly, the cathode ray tube, which consists of an evacuated chamber with two electrodes, one electrode that we call the cathode and the second electrode that we call the anode. Prior to 1897, of course, you guys know that there was this mysterious beam that was leaving the cathode going towards the anode, going through a little hole in the anode, and then striking the screen straight across from that. These mysterious beams were called cathode rays because nobody really knew what they were, other than they were these things that left the cathode, whatever they are. Thomson comes along and figures he can do a little analysis of this, throw a little twist, a couple little twists into this, and maybe determine what these cathode rays are. So he first first introduces a magnetic field over here on the end of it, right? And this magnetic field does what to these mysterious cathode rays? It pushes them down, it bends them, right? So it causes them to go from a straight line path to a curved path, something like this. And then he says, well, look, I can do an analysis of this. We've known about this analysis for charged particles in magnetic fields for decades. He knows they're charged particles now, right? He knows they're negatively charged particles because that's the only thing that's going to deflect in a magnetic field like this. So he starts doing that analysis. He says Fc is equal to Fm, right? Centripetal force equals the magnetic force. The shape of the path is a circle, always caused by the magnetic force QVB. So we'll say mv squared over r equals QVB. Cancels out of v. Doesn't know what m is. Doesn't know what v is. Does know what r is. Okay, he's good for that one. Doesn't know what q is. Does know what b is. But he's got three unknowns here. M, v, q. How does he get one of those unknowns? Which one of those unknowns does he end up getting? Which one of them does he end up getting? What was it? For b? V? Yeah, he ends up solving for V, yes, using not the acceleration chamber over here, although technically the acceleration chamber over here, we could say EI equals EF, right? We could say QVI. V, by the way, is not speed. V is electric potential difference, right? VF is or EF, I should say, is 1/2 mv squared. We could technically solve for VF here, but we've got a little bit of an issue with that. And the issue with this is, number one, it's not necessarily the speed the particles are moving, it's the maximum possible speed they're moving. We want the exact speed they're moving in this chamber, not the maximum possible speed. The other issue is we don't know what Q and M are, right? So if we look at it this way, all right, we've got two equations and we've got three unknowns, Q, M, and V. So that's not going to be overly helpful to me, not yet at least. So he does need to find V, but how is he going to do it? Not by looking at the acceleration chamber, but by looking at the non-existent thing, or at least as I have it drawn right now. Yep. The velocity selection chamber, which consists of a magnetic field and an electric field. The magnetic field would cause a downward force. The electric force would cause an upward force. Sometimes one force is bigger than the other, depends on the speed of the particles. But if the speed of the particles is just right, what happens? The speed of the particles is just right. They're going to go straight through. And when they go straight through, we know that the magnetic force that acts downwards has to be equal in magnitude to the electric force that acts upwards. So we're going to say QVB is equal to Q times E. Q's cancel. V is equal to E over B. So now this is good, because now I've solved for a speed of the particles. Not all of them, but all the ones that go straight through. And those ones that go straight through are the ones that go into this main chamber here. So we know the ones that go into this main chamber down here have a speed of E over B. Now I can find that speed. Plug it into here. Still have two unknowns, but that's okay, because now at least it enables me to find a ratio, the charge to mass ratio. And that number worked out to be for an electron 1.76 times 10 to the 11 coulombs per kilogram. What was special about that number? Yeah, this is it's a special number, right? Rosie, what was so special about it? Yeah, yeah, good. It's so big, right? You find the charge to mass ratio of this, of that, of this other thing. Nobody ever found a charge to mass ratio that was that big, which means if that number, Q over M, is really, really big, in fact, bigger than anything else ever found, then M must be smaller than anything else ever found. In other words, it's smaller than an atom. It's not only a negatively charged particle, it's a subatomic negatively charged particle. And there's the discovery of the electron. He didn't know what Q is, didn't know what M was. That's okay. He still established that we had a negatively charged subatomic particle. Now, let's look at the oil drop experiment. The oil drop experiment had two charged plates. Okay, with the way that I have it drawn, the top plate would be what? Negative or positive? It'd be positive, and that's because the side of the battery that's closest to it is positive. This side would be negative. Although you could easily see that reversed. Okay, the oil drop experiment could be easily set up the other way. We inject these oil droplets, these tiny little oil droplets, into this space between the parallel plates. We use an atomizer. It's like a perfume dispenser. Makes the liquid into this tiny little mist. These tiny little particles in between here, some of them are charged positive, some of them are charged negative. Some of them may not be charged at all. In fact, we may need to actually expose it to X-rays to cause these oil droplets to become charged. With the X-rays, we can actually ionize them to become charged oil droplets. Regardless of how we cause them to become charged, most of them become charged. Then we look at the forces acting on each one. We look at this one that has an electric force acting down and a force of gravity acting down. In this one, we have a gravity force acting down and an electric force acting up. People all the time mix this up with the velocity selection chamber over here of the cathode ray tube. It is not the same thing. Not at all. In the cathode ray tube, we have Fe equal to Fm. Here we have, well, if we're looking at these particles right here that are suspended, we would have Fe equal to Fg. Fe equal to Fg. Why did we not include gravity over here? Gravity was acting on these electrons as they went between these two plates. But the force of gravity on a single electron is so small compared to the electric force or the magnetic force that it just didn't matter. We just didn't need to include it. The force of gravity on an oil drop is not so small. It's a lot smaller than the force on a baseball, okay, but it's still significant enough that we have to account for. So we're going to say Fe equals Fg. Q times E equals M times G, and then we usually rearrange this to solve for Q. We get mg over E. What do we get for a charge there? Well, it could be any one of a number of things. But we knew that it had to be, we know that it has to be a number, a whole number, times 1.6 times 10 to the minus 19. So it could have been twice that, which is 3.2. It could have been 300 times that, which is 4.8 times 10 to the minus 17. But it had to be a whole number times 1.6 times 10 to the minus 19. The big deal with this, as opposed to the big deal with this, right? Big deal with this is it's so big that the mass had to be so small, it was subatomic. The big deal with this is that we had, number one, an elementary charge. You can't get smaller than that charge. It's as small as it gets, 1.6 times 10 to the minus 19. Therefore, it must be the charge of an electron. Second thing is, charge is, remember that word? Charge is quantized, which means that the charge can be a certain value or it can be a whole number of multiple of that value. Okay. Now we could say that money is quantized. In Canada, you can have 5 cents, or you can have a whole number multiple of 5 cents, but you can't have anything in between, right? You can't go to the store and pay $1.93 anymore. You pay $1.90, or in that case, you would pay $1.95. Money is quantized. Charge is quantized. You can have 1.6 times 10 to the minus 19 or any multiple of that, but you can't have anything in between. You can have 5 cents or any multiple of that, but you can't have anything in between. Got it? All right. We had 2 questions, I believe it was, on the oil drop experiment, both involving suspended oil drops that I want to take a look at right now. They were on page 763. Now, both of these involve oil drops that are suspended, which means that we're going to set, in each of these cases, Fe equal to Fg, like we did in our review a second ago. But remember, Christian, another term that could mean the same, doesn't mean the same thing as suspended, but we do the same thing to it as if it's suspended. Constant velocity. If these oil droplets are going up or down at a constant speed, we set Fe equal to Fg. Not Fe equal to Fm, like the cathode ray tube, but Fe equal to Fg. Let's take a look at both of these questions, okay? I don't think finding the charge is so difficult. Honestly, I think it's dealing with the number of electrons gained or lost and the direction of the electric field that becomes challenging here. Number 1 says, how many electrons are gained or lost by a plastic sphere? Using plastic spheres here instead of oil droplets because it's less messy. When I was in my 3rd year university, I did the Millikan oil drop experiment. I repeated it with some lab partners, but we weren't lucky enough to get to use these little plastic spheres that people use now to perform this experiment. We used oil, and it was a absolute nightmare of an experiment. It was a nightmare. I bet it took 4, 5, 6 hours to get data, to collect the data for this experiment, and then I have no idea. I don't even remember how long it took after that to actually do an analysis of this. It was a nightmare. It becomes much less of a nightmare now if you're using plastic spheres because they're nice uniform shapes and because they're way, way, way less messy. Regardless, the analysis is the same. It's suspended in an electric field pointing upwards. Let's draw a picture of this. Here's my oil drop. We know we have a force of gravity acting down and an electric force acting up. How do we know those 2 forces are in opposite directions? How do we know they're in opposite directions? Yep, Adele? Yeah, if it's suspended, you can't possibly have them acting in the same direction. Otherwise, it's going to accelerate in that direction. Now, we know we have an electric field pointing upwards here. We want to find out how many electrons are gained or lost. Let's do our analysis here. Fe equals Fm. We're going to say Q times E is equal to QVB. No, that's wrong. F equals Fm. What am I doing? Exactly what I told you not to do. Fe equals Fg. Okay, this is not the velocity selection chamber of the cathode ray tube. This is the oil dropper experiment. QE equals M times G. Rearrange this to solve for Q. I get mg over E. When I sum in my numbers here, I should get a value for charge of 4.8 times 10 to the minus 19 coulombs. Now, that's not what the question said. The question didn't say what's the charge. It said how many electrons have you gained or lost? How many? A number of electrons. Take the total charge and divide it by the elementary charge, the charge for 1. There we go. We have 3 electrons. Now, gained or lost? Tell me whether this oil drop is positive or negative. Look at your picture. Look at the picture, nothing else. Is this oil droplet positive or negative? Forget about gained or lost. Forget about anything else. Positive or negative oil drop. Adele? How do you know? Good. Back in Unit 2, we learned that the electric force will be with the field if it's a positive particle. If it's a negative particle, the field, the force will be opposite to the field. You guys remember that? This has got to be a positive charge, therefore it must have lost 3 electrons. If you're neutral and you lose negatives, you become positive. Okay, how many people got that? Good. The whole thing, I mean, right? Like it's important not just to recognize the whole 4.8 or 3 there. It's important to recognize that it was electrons lost as well. Okay, second question says, what electric field will suspend, again, this is always good when we see it suspended because it makes it easier for us. It's the only thing we know how to do right now. But even when we learn how to do accelerating particles, it's still easier when it's suspended. Here's my oil drop. We have a plus charge here. It's suspended, so I know Fg is downwards and Fe is upwards. What's the electric field? We're going to say Fe equals Fg, not Fm. Qe equals mg. We're always going to set it up like this, right? If it's suspended or constant speed. Solve for Q here. Sorry, solve for E here, I mean. I get mg over Q. When you do the math there, I think it works out to be 9.8 times 10 to the 5. There we go. Up or down. How do you know the electric field is up here? Go to your diagram. That's why we draw our diagram. Ethan? Good. And a positive particle, the force is always in the same direction as the field. If it was a negative particle, the force would be opposite to the field. So we know the field's got to be upwards because we know the force has to be upwards, and we know that it's a positive particle. So it's an upward field. All right? If you replace that with a negative particle, you get the same answer, 9.5 times 10 to the 5, 9.8 times 10 to the 5, except the field would be downwards, right? And in question number 1, if you replace that with an electric field, if you replace that with an electric field that was downward, let's say, then you would have to have a charge of 3 electrons gained to give it a negative charge instead of a positive charge. All right? All right, let's take a look at what happens when we have oil droplets that are accelerating. And maybe they're accelerating because we have 2 forces downwards, an electric force and a gravitational force, or maybe it's because we have an electric force upwards that's way bigger than the gravitational force downwards, or maybe even because gravity is bigger than the electric force. Regardless, we have accelerating charges. I have 3 diagrams on the board right now that should, hopefully, put you in mind of the next step that we're going to follow to solve these problems. Think back to physics 20, think back to a little bit of physics 30. What are you going to do next? Simply based on what you see on the board right now. Ollie? We've got our free body diagrams drawn. Okay, what do you do after a free body diagram, Ollie? Okay, well, once your mood improves, then I'm not going to say F equals G because they're not balancing each other, right, Jason? Good. F net. We're going to say F net is equal to the sum of the forces. That would be Fe plus Fg. Now, technically, even where they're suspended, we're still technically doing this, but the net force is 0 when they're suspended. Therefore, the magnitude of Fe will just be equal to Fg. Now, once we write down F net is equal to the sum of these forces, which we did a million times in physics 20, and we've done as well in physics 30, remember with Coulomb's law with 3 charges in a row? What next step? It's the next step that we always write down. F net is the sum of the forces. MA is also the sum of the forces. No, that's it. Solve for Q. A little bit harder to solve for Q now. My suggestion here would be probably sub in your numbers and then rearrange. Make sure you pay attention to signs, positives and negatives. We're not making something positive or negative because it's a negative charge. We're making something positive or negative because of a direction of a force. Okay. In the first case, Fe would be negative, Fg would be negative. In the second case, Fe would be positive, Fg would be negative, Fe would be positive, Fg would be negative. If you're told it's accelerating up, A will be positive. If you're told it's accelerating downwards, A will be negative. Yeah, Christian? Well, as I said, I would suggest you plug in your numbers and then rearrange this one. But if you wanted to rearrange it first, you get MA minus MG over E. I think the problem with that, Christian, is that we end up getting mixed up with signs when we do that. I have no issue with rearranging before we sub numbers in, because that's what I almost always do, right? But in these questions, I think you end up messing up the signs. And you end up getting a wrong answer as a result of that. So just sub in your numbers into this equation with the signs and then worry about rearranging. Okay? Let's take a look at this one on page 764. It says a tiny plastic sphere of mass 8.2 times 10 to the negative 15 is placed in an electric field downward with a vacuum within a vacuum chamber, 10 excess electrons. Determine whether it will accelerate and if so, in which direction. Okay, I think we have to assume that it does accelerate, right? If we're wrong, and we solve for acceleration, what are we going to get for A? If we assume that it accelerates, but we're wrong, and we solve for acceleration, what will be, Emma? 0. Okay, so no big deal. I think it's going to accelerate. I'm going to say that it does. I'm going to solve for acceleration, and then if I get 0, oops, I was wrong. No big deal. All right, let's draw the picture, because we always like to draw the picture for these, or at least I always do, and you should. There is an electric field downwards. Tells me it's 1.0 times 10 to the 5. There is a charge that is negative. How do you know it's negative? How do you know it's negative, Ethan? Right? Extra electrons. We have a downward force of gravity acting on it. There's an electric force acting which way? How do you know it's up? Good. The electric force is opposite to the direction of the field if it's a negative particle. Now, I don't know how big I should draw that. I don't know whether it's bigger or smaller than the force of gravity. We're not going to worry about that right now. We know it's upward. Okay, we're assuming it accelerates, so we're going to say F net is equal to the sum of the forces. If we knew for sure it did not accelerate, then we just set Fe equal to Fg, correct? We assume that it does accelerate, though. F net is equal to Fe plus Fg. The net force is m times A, which is QE plus mg. M is 8.2 times 10 to the minus 15. We're solving for the acceleration here. We want to see if it's 0 or not. Q is 1.6 times 10 to the minus 18 because there's 10 extra electrons. And the electric field is 1.0 times 10 to the 5. Here's the mass again. Times it by 9.81. We're not going to worry about a sign for F net because we're solving for A. We're going to make the electric force positive despite the fact that the field is downward. The force is positive because the force is upwards. So we draw a picture, right, to make that simpler to see. Gravity, however, is downwards, so we're going to make that a negative term. We're going to say 1.6 times 10 to the minus 18, it's the charge of the oil droplet, times 1 times 10 to the 5. It's a positive number. Let's subtract from that, brackets 8.2 times 10 to the minus 15, times 9.81. Gives me the right-hand side there. I'm going to divide that by 8.2 times 10 to the negative 15. Gives me 9.70. Okay, does it accelerate? Does it accelerate? Yes, because the A is not 0, right? Does it accelerate up or downwards? Cal, did you say it there? Upwards, how do you know? Good, because A is positive. Good. Now, do you see how useful it was once again, for the 4th time in a row now, to draw a diagram? Okay, this diagram allowed us to determine that the electric force is positive. Okay, in the absence of this diagram, we're probably going to make the electric force negative because it tells me the field is negative. It's a negative particle, the force is opposite to the field. Yeah, absolutely. 1.6 times 10 to the negative 18, that charge comes from this statement here where it says the sphere has 10 excess electrons. So if it has a charge of 10 electrons, then it has a charge of 10 times 1.6 times 10 to the minus 19 coulombs. And when you multiply 10 by 1.6 times 10 to the minus 19, you end up getting 1.6 times 10 to the minus 18 coulombs. Does that make sense? Good question. Anybody else? Okay, let's have a look at those two questions on 764, please. I want to draw the free body diagrams for question 1 and 2 here. And then I'll give you guys another minute to solve what you need to solve here, okay? Number 1, everybody just look up here. Number 1 says find the net force on a sphere that's negative. It's a negative charge. The electric field is upwards. Gravity is always downwards. If it's a negative particle in an upward electric field, then which way is the electric force? It's going to be downwards. The electric force has to be opposite to the field. Okay, that's helpful to know that they're both downward. When we go to sub in our numbers for electric force and gravitational force, we make them both negative. In question number 2, we're reversing the direction of the electric field. So the electric field is now downwards. That makes the force of gravity downwards and the electric force upwards. Now, they don't necessarily balance each other, but we know that the electric force is going to be opposite to the direction of the field. Now, when we go to do question number 2, F net is equal to the sum of the forces. Fg will be negative, but Fe will now be positive, right? And as I said, the answers that they give us here are both incorrect. Give you another minute to finish those off, and then we'll move on. All right, these 2 questions will be your homework, in addition to these questions on page 767. So 767 and 764 are homework for tomorrow.